Okay, welcome in everyone. Today's topic is going to concern itself with probability. More specifically, it's going to be concerned with mixed probability, the kind of the way or approach that you would see on the AP exam. They don't just keep to nice little tight things like, okay, today's this problem will be basic probability. Oh, and then this next problem will be binomial. Oh, and this one will be a random variable. No, they're going to give you a scenario and then expand it out so that they include as much probability as they possibly can. So let's start out with this problem here. This problem is problem number 5 from the 2019-2020 administration, or at least it was until the pandemic hit. So let's just look it over and see what we've got. It says, for each day that Sasha travels to work, the probability that she will experience a delay due to traffic is 0.2. Each day can be considered independent of each of the other days. All right, so they give you a fixed probability, and she will either be delayed or she won't. So this is sounding very much like binomial, okay? So let's look at the first part. It says, for the next 21 days that Sasha travels to work, what is the probability that Sasha will experience a delay due to traffic on at least 3 of the days? All right, 3 out of 21. Trials are independent, fixed probability, fixed number of trials. I mean, it's looking very much binomial. So let's just go ahead and indicate that, because this is what AP wants. So let's say that X is binomial with n equals 21, and probability of a delay is constant at 0.02. Now that takes care of a lot. It's telling the reader that we know what's going on, that we know what the question is asked, and how we're going to approach it. Now, there are formulas, and you have a formula chart, and the key, which I'll show you in a little bit, has formulas all filled in. But let's just proceed the way that we normally do it. So this is the probability that X is at least 3, so that'd be greater than or equal to 3. And we know that this will be a binom CDF, right? Because 3 or 4 or 5 or 6, not just one thing. And so N is 21, P is 0.2. And the lower boundary is 3, and the upper boundary is 21. Pop that out of the calculator, and you get 0.8213, which, by the way, is correct. So box it up there so that the reader can see it and see all of our work. Let's count that as done, okay? So then B, I'm guessing, will be a little different because it's a probability question, and we've already done binomial. So it says, what is the probability that Sasha's first delay, we've seen that before, due to traffic will occur after the 5th day of travel to work? Okay, when does the first success happen? That's geometric. So we don't have any shorthand for it, but let's just let the reader know that we know what's going on here. So we'll write this out, and then we'll just do the problem. All right. So after the first or the 5th day rather of travel, this is the probability that X is greater than 5, and this will be geomet. Oops, sorry, left the letter out. So this is geomet CDF, and the probability is 0.2. And the lower bound here is going to be 6 because we're not including the 5, right? It's after that, it's beyond that. And then just some big number. You can put an infinity here if you want, or you can put a big number. When you type it into your calculator, let's just put in like 10,000 or something like that. And that will give us 0.3277. And that is actually correct too, all right? So while we're at it, let's just look at the scoring guideline. And I think I can just do that by putting this minimized and opening this. Okay, so intent of the question, primary goal of this question, goals of this question were to assess a student's ability to recognize a situation in which a binomial probability distribution may be applied. Okay, bingo. 2, discuss conditions for accurately using a normal approximation to a binomial probability and compute appropriate binomial probabilities. All right, well, we'll see about, numbers 2 and 3, well, at least number 2. But definitely number 1 and number 3 here. But look how they did that part A. All right. This is the number of delays. It's 1 minus the probability of no delays plus the probability of exactly 1 delay plus the probability of exactly 2. All right. So that's the way they proceeded. And look, they've got the formulas here for binomial. All right. See, it's got the what's the word I'm thinking of? The combinations and probability of success, probability of failure, all that stuff. And they got a right answer. So they actually did this differently than the way we did. So let's see if we are okay with the way we did it. So part A is scored as follows, essentially correct if the response satisfies the following 3 components. Clearly indicates a binomial distribution with n is 21 and p is 0.2. We did that with the shorthand. Indicates the correct boundary value and direction of the event. Within our binomial CDF, we had the lower and the upper bounds, and we had the right answer, okay? Yeah, but we didn't do it the way they did it, so are we going to get away with that? Let's see. I think it's okay. We can say the response of, and they're doing it again differently because I guess this is like the old style calculator, like the 84. 1 minus binomial CDF, n is 21, p is 0.2, upper bound is 2. All right, that's given and essentially correct. And I think given that we have the new calculator and that we've set it up, the way we did, I still think that we're essentially correct. Now, if you feel like we should be a little bit more aligned with what they do, you can just maybe do this and say that's lower bound, and that there is the upper bound. And now they can't argue with it. They don't like the calculator speak. But you know what? At the same time, we did everything basically that they wanted. So, if you want to be a little bit more precise, you can. Now, we did ours here as a geometric for letter B. They didn't. All right? They did theirs. Let's look. Probability that Sasha's first traffic delay will occur after the 5th day is the probability that no traffic delays occur on any of the first 5 days. Well, in working with geometric, we know that it's like a fail, a fail, a fail, a fail, and then success, success, success. Or maybe I left out a day, but you get the idea. So they just went ahead and did it. The probability of no delays during the first 5 days is 0.8 raised to the 5th. And they got the same answer. We would get full credit for this. All right, now for C, let's see. Let me go here. I think I'm going to need to pause for a second. Hold on. Okay, here's part C. And we're actually not really ready for this. This is coming next week, all right? I'll go ahead and show it to you anyway. It says, consider a random sample of 21 days that Sasha will travel to work. For the proportion of those days that she will experience a delay due to traffic, is the sampling distribution of the sample proportion approximately normal? And justify your answer. All right, you would have no way of knowing how to answer this, but I am going to answer it for you, and maybe it'll resonate a little bit with what we had, for conditions for a normal approximation. All right, so this is what I wrote for mine. So for a sampling distribution, All right, if you're watching this, speed it up. If you're watching it on normal speed, for proportions, to be approximately normal, all right, sorry, that's kind of boring. All right, here goes. This should look really familiar. Both n times p and n times 1 minus p must exceed 10. Whoops, must exceed 10. Remember we had this for our normal approximation? That was a condition. It's a condition for this. Well, when you do the work, 0.2 times 0.21, times 21 equals 4.2. Whoops, that's kind of way below 10. All right, but I just went ahead and did sort of a complete job. So then it would be 0.8 times 21. And the two have to add up to 21. So you could actually subtract that from 21 to get the other product, but just go ahead and show it. All right. So since not both exceed 10, the sampling distribution is not normal. Is not normal. All right. So the reason I had you sit through that excitement was because I need you to see the formality in the answer. Plus, this particular problem is one of the 13-minute variety questions. That's what 5 of them are. And then the 6th one would be about 25 minutes. And honestly, we can get through this thing in probably 5 minutes tops, maybe a little longer if you write slowly. But then we'll have extra time left over that we can use for harder questions. So now you've seen that, I'm going to move on to another example. So allow me to pause. Okay, our next example is on page 13 in your packet. And I can't recall which year this showed up on the AP exam, but it is an AP exam question. It reads, golf balls must meet a set of 5 standards in order to be used in professional tournaments. One of these standards is distance traveled. When a ball is hit by a mechanical device, iron Byron, why do people write these things into the questions? Anyway, with a 10-degree angle of launch, a backspin of 42 revolutions per second, and a ball velocity of 235 feet per second, the distance the ball travels may not exceed 291.2 yards. All right, the issue here is that I guess you can turbocharge a golf ball to where it becomes no longer competitive because even people that don't swing really hard can launch it pretty far. So in order to make the game more reasonable, they've put an upper limit on how far the ball can go. So manufacturers want to develop balls that will travel as close to the 291.2 yards as possible without exceeding that distance. A particular manufacturer has determined that the distances traveled for the balls it produces are normally distributed. Okay, yeah, so that's important right there. Normally distributed. I bet we'll be using that with a standard deviation of 2.8 yards. All right, so if they wanted to travel as close to 291.2 yards, then that's probably going to be mu. Okay. Now there's a whole bunch of other numbers here that I think are just distractors. I don't think we need about the revolutions per second or the velocity in feet per second. Maybe in some other problem, but not here. So if the manufacturer sets the mean distance traveled equal to 288, all right, well, maybe this isn't mu. Well, this is mu now, so that's mu. what's the probability that a ball that is randomly selected for testing will travel too far? I'm going to get rid of this. This was probably a bad idea. All right, but too far is anywhere beyond 291.2. And it looks like this is just going to be a standard normal calculation. So let's draw it out, because remember, the AP people like that. All right, so they say this is centered at 288, and they're wanting to know the probability of going too far, and that'll be 291.2. All right, so we can just say that X is approximately normal with a mean of 288, at least in this problem, and a standard deviation of 2.8. And that's, again, the shorthand notation that they like. Now we can just go to calculator speak. Okay, so we want, that region there, the probability that is represented by that region. So this is the probability that X is greater than 291.2 yards. And so we'll need to standardize. That's the probability that Z is greater than, that's X, 291.2, minus mu, that's 288, over sigma, which is 2.8, right? And if you want, you can get the z-score and do a normal CDF from there to infinity, or you can do what we pretty much typically do and shortcut this. So this would be normal CDF. All right, so we are going from 291.2 up to some infinity, so let's just go 10,000. The mean is 288. And the standard deviation is 2.8, and that should give us about 0.1265. So that's the probability of seeing a golf ball go farther than they want it to. Okay, let's go on. So let's set up for B here. Assume the mean distance traveled is 288 yards and that 5 balls are independently tested. Oh, 5, okay. So they either go too far or they don't. What's the probability that at least one of the balls will exceed the maximum distance of 291.2 yards? Well, it either will or it won't. So, and it's definitely got a fixed number of trials with 5. So this is binomial. So let's just go ahead and use the shorthand notation for this. X is binomial with, let's see, n is 5. And we need a probability. But didn't we just get that probability? So that'll be 0.1265, all right? And that at least one will go. You could do 1 minus the probability that none will. But let's just go ahead and do it sort of the easy way. So this is binom CDF, because it could be 1 or 2 or 3 or 4 or 5. This is 5. Probability is 0.1265, and we're interested in either 1 at the low end or up to 5 at the high end, and I think we can just write this out. This is 0.4915. By the way, both of those are correct, and we started with normal here and we went to binomial here. All right, so that's pretty good. We got most of the problem right. If the manufacturer wants to be 99% certain that a randomly selected ball will not exceed the maximum distance of 291, what is the largest mean that can be used in the manufacturing process? All right, now we're trying to find a mean, and it's certainly not binomial here. So I think we're back to a standard normal calculation, but this is going to be x minus mu over sigma equals z. All right, and we're looking for the mean. All right, so let's kind of draw this thing out. And they want to be 99% certain, right? So that's your lower 0.99. And then, there's that 0.01 that's left over to make a full 1. So we need a z-score at that cut point. So that'll be an inverse norm, or you can look at the table and figure it out from there, and that'll be 0.99 because it's not the 0.01 we want, to go from left to right. And you need a positive z-score, so that's 2.3263. You can truncate that a little bit, but I like the extra accuracy. So x, 291, oops, that's my dyslexia hitting again. So 291.2 minus the mean, which we don't know, because we're kind of customizing the process at a certain mean to reach this standard. So that's over 2.8, and that's going to equal 2.3263. Because it says, what is the largest mean? It doesn't mean like what range of values are we looking for. The is a single number. So that's not an inequality, right? So multiply each side by 2.8, then subtract 291.2, and then fix the negatives, and you're going to get mu equals 284.686. There I go again. 0.686. And remember, this has units, so yards. And that is correct. So that's not probability, but they did mix in, something related to it. So I'm going to pause again. All right, so I got one more for you. This last one is from the 2014 administration, and it's question 3. So here we go. We won't do all of it because one part of it we're not quite ready for, but it reads that schools in a certain state receive funding based on the number of students who attend the school. To determine the number of students who attend a school, one school day is selected at random, and the number of students in attendance that day is counted and used for funding purposes. The daily number of absences at high school A in the state is approximately normally distributed with a mean of 120 students and a standard deviation of 5. So figuring we're going to be getting some of these normal questions, so let's see what we get. So A, if more than 140 students are absent on the day the attendance count is taken for funding purposes, the school will lose some of its state funding in the subsequent year. Approximately, what is the probability that high school A will lose some state funding? All right, so this one is where we're going to use that normally distributed setting. All right, so X is approximately normal with a mean of 120 given in the problem and a standard deviation of 10.5. All right, so we'll just draw a curve. Again, AP people really do like that. So here it is. So 120, and so it's if more than 140 are absent on the day the attendance count is taken for funding, the school will lose some of its state funding. Oh, we already read that. So anything at 140 or higher is a hit on their state funding. So they want to know what's the probability they'll lose money for funding. All right. So this is the probability that X is greater than 140. And it's the usual old standardizing thing. So the probability that Z is greater than 140, that's X, minus mu is 120, over sigma is 10.5. And I just went ahead and shortcutted this. You don't have to. This will be normal. C, D, F, and 140. And it goes to infinity, right? So somewhere out here is infinity. We'll just go to 10,000. That's good enough. And 120 for the mean, and 10.5 for the standard deviation. And that'll give us 0.0284, which is correct. All right. Okay, now the next one is a random, not a random variable question, but a sampling distribution question. And it's beyond what we know now. In a couple of weeks, we will be able to answer that. So we're just going to skip it and go on to C. Excuse me. Typical school week consists of the days Monday, Tuesday, Wednesday, Thursday, and Friday. Yeah. The principal at high school A believes that the number of absences tend to be greater on Mondays and Fridays. That's probably true. And there is concern that the school will lose state funding if the attendance count occurs on a Monday or Friday. If one school day is chosen at random from each of 3 typical school weeks, what is the probability that none of the 3 days chosen is a Tuesday, Wednesday, or Thursday? All right, I took a little bit of a different approach to this than what they asked, but I got the right answer. All right, we're not ready for B, so let me get rid of that. We're doing C. All right, so let's just say probability, and I'm going to abbreviate this. I do have it written out on my key, and this is just for a week. So for a week, it's not all 3. So the probability of a Tuesday, Wednesday, or Thursday, I guess, let me go back. Oh, that's not what I really want. That's not what they were asking. Probability that it's not, that's better, Tuesday, Wednesday, or Thursday. HURS. Isn't that the same as the probability that it is a Monday or a Friday? Okay, same thing. All right, so now instead of working with 3 things, we're working with 2. So probability of it being a Monday is 1/5, and the probability that it's a Friday is also 1/5. So the probability that it's Monday or Friday, that's going to be 1/5 plus 1/5, because or means plus, which is 2/5. Okay. All right. So for 3 weeks, all right, from each of them, so that would be the first and the second and the third. All right, so now we're back to and. It's the probability of the first and the second and the third. All right, and means to multiply. So any given week is 2/5. So 2/5 times 2/5. Whoops, make that a 5. Times 2/5. That's going to be 8/125, which is going to be 0.064. Okay, so they went from normal just to regular old probability calculations. That's not all the options that we could possibly have. There could be other things. But what I want you to do is just take the worksheet that I have posted up in the announcements and I'm passing out to the kids in class and work it. The key is posted. Let's see how it goes, and just get used to answering, kind of formally like this, and that you can pull all of those things that we learned in probability out of your memory cells and put them into practice. So that's it.